If you need to do so, that's fine, yes.
Check, check, check. It was working. I hope it's... Hello, hello.
I suppose we'll see when it starts recording. Starts recording, we'll see what we get. Does that make sense? So yesterday, or Monday, we were taking an X and a Y and finding an R, right? Now we're just doing the opposite. They're giving you something that's moving in both X and Y, and you're breaking it into its X and its Y pieces. They're giving us the green now, and we're breaking it into the X and the Y. So that we can simply add a bunch together, right? If I had two vectors that were going both north, I could add them together to find out how far it went, right? But if I have them in different directions, that's difficult. How do I know how to add them? I add them by breaking them into their components and putting those components together. Sure. Yeah. And of course, we're making 90 degrees, right? So all of these will just use Pythagoreans. Does that make sense? We don't need to use law of cosines or law of sines because we have a 90-degree angle between these guys. Matt, did you want lunch? I did, actually. But you all were just chatting. Did you want lunch? That's fine. You did not tell me yes, but that's fine. All right. Flip over onto page 126 and 127 for me, if you would. They're giving you that brief reminder about trigonometry. That sine of theta, how do I find sine? Good. Opposite over hypotenuse. And if I want to do cosine of theta, it would be adjacent over hypotenuse. And we'll use tangent in a moment, but these are the two that we will want to be aware of. Right? Sir?
Opposite of what, though?
It's the opposite from the angle theta.
So you see the angle, I just do the opposite of it?
Mm-hmm. Yeah. Right? So if I know this angle, if this is my theta, right? Hypotenuse is always the one opposite of the 90 degree, right? Always. But how do I know, is this adjacent or is this adjacent? How do I know? The one that's connected to that theta, right? So in this case, this would be my adjacent, and this would be my opposite. But if I knew this guy, are you comfortable? Hypotenuse stays the same. It's always opposite the 90 degree. But now this becomes my opposite, and this becomes my adjacent. Cobwebs coming back. Oh, yeah, no, I know this stuff, right? Good. Physics, we use this when we're talking about an x and a y graph. We always make this our 0 starting point. And we go this direction so that this is 90. And this is 180. And this is 270. And now we're back to 360. Okay? Remember when we did the cardinal directions, it was turn 90 degrees. That 0 was on north. But in physics, as well as in a lot of the other classes you have done, we start on that x, that positive x-axis as being our 0. So when they give you a number for an angle, that's what they're speaking about. Does that make sense? And they number those quadrants, 1, 2, 3, and 4. I'm not too worried about that. We don't use that. But you must be comfortable with this. If I have a vector that's going in this quadrant, change color. If I have a vector in this quadrant, are you comfortable this y is positive and this x is positive?
Yes.
Okay? Are you comfortable that if I put it over here, my y is still positive, but my x is... Does that make sense? Okay. And you can, of course, make the same pieces down here. Down here, sorry, different color. This would be what? Y is negative and x is negative. Cool. And I'm running out of colors, but we'll use this one. How about this one? Y is negative, but the x is... Does it make sense? And so we could label them accordingly. Again, I think this is all pretty well reviewed for you, yeah? You've heard this stuff before? Good, good. All right. So, look on 127. They show you that if I have a bunch of vectors, right? I'll kind of try and draw what they have. They've got one vector going like this. They've got one vector going like this. They've got another vector going like this. Right? That's in the very top of 127. You can take, and we can put all of those vectors together. Notice I can't change their angles, right? The angles have to stay the same. Right? I can put them together. My hand's blocking the way, sorry, I can't make it go exact. And now what we're saying is that this guy is going over this far, right? And going up that far. Does that make sense? I could have found the x for this guy, the x for that guy, and the x for this one. And then the y of this guy, the y of that guy, and the... Does that make sense? I'm simply putting these guys together. This is A, this is B, this is C. So this is AX, this is BX, this is CX, this is AY, BY, CY. So I can simply just add the components of each of those vectors together to find the sum of the whole thing. Does that make sense? Okay, okay. Again, all I'm doing is for each one of these, for A, just like we did here, I'm taking one vector and breaking it to its x and its y. But I'm just doing it for all three of them together. You don't have to draw it where you add them like this. You can simply find x and y of A, find x and y of B, find x and y of C, and then just simply add those pieces together. That's fine. Are you there? Okay. So are you comfortable that this would give us a resultant that looks like this? That green would be my resultant. Remember, the resultant is just the addition of all of the pieces together. So you can go on 50,000 turns and twists, but in the end, you end up here from where you started. Okay, how far over, how far up do I have to get to that point you ended at? That's what the resultant is. All the purple equaled basically starting here and going there. Even though I twisted and went up and then over and then up, this is the actual resultant of what I did, the displacement of what I did. Okay? So the resultant would simply be, remember, because r squared equals a squared plus b, or let me use x and y. R squared would simply just be x squared plus y squared. Would give me r squared. All of these plus all of these would give me r squared. Does that make sense? And the last thing, if I want to find this angle, because that would be my theta, right? Does anybody know how I would do that? Because in this case now I know x and I know y, but I don't know. So I know the adjacent, I know the opposite, but I don't know the hypotenuse. Ooh, do you remember what I would use? I'd use tangent. Absolutely. And they show you that equation there on page 127. But if I want to find theta, I got to write a different spot. I don't have enough room here. That theta is going to be equal to, and again, you see it there on page 127, the inverse tangent, and it's just like sine. It's just like a slope. It's rise over run. It's ry over rx. In other words, all of this x and all of this y added together. And on your calculator, when you plug in, you can't just push tangent. You have to do the inverse tangent. I mean, usually it's a second tangent. You'll see it on your calculator. And that will give me the actual angle that that tangent is going from the x-axis.
So you would plug it into the first equation, r squared equals?
Right, this would give you the amount. Right? It would give you this r, this displacement, how far it went. And remember, these are vectors, so vectors have to have both magnitude, an amount, and a direction. So here's our amount. Let's say that was 15, the r. But we have to know what direction is it going. And so that's what the theta is for, to give us that angle. Right, the total of all of these x's would be here. The total of all these y's would be there. Yes? Sorry, go ahead.
What is the little O thing for theta?
Theta. Yeah, it just means the angle.
Would we be given the theta, or would we have to?
No, you would have to find that guy. Because we want to know with this resultant, right? We've gone some way over and some way up or down. We want to know what angle is that, so that we can give a direction to it. It could be. It all depends on the height of these guys, right? If I only go over a little bit but super up, that's going to be a very steep angle, right? If I go way over and only a little bit up, it's going to be a very small angle. Does that make sense? So it just depends on your x and y. Yeah, because we're breaking it into its x and its y. That's absolutely correct. So that's why we're just using Pythagorean's theorem and not have to use law of sine or law of cosines. Yeah, good question. Are you with me? Whew. All right. What I would love for you to do, and I can't rush through without pointing this out, on the bottom of page 127, they walk you through in very solid detail what are the steps you use to solve these vector addition problems. On 127, on the very bottom, problem solving strategies. Using the following technique to solve problems. So what you have there is exactly what we just did here together. All right? I want to make sure you see that. They show you how to do that on the example problem number 2. We've only about 10 minutes, so I'd love for you to do some work here. And if you have questions about that, please feel free to ask. I'm looking for you to do in 5.1 on page 129, and it's numbers 5 through 9. Rock and roll.